Perfect. Hi, I'm Avery Conner, a PhD candidate at University of Oregon, and might as well go on right into it. Next, please. First, I would like to thank everybody that's helped me on my research and projects through the years, specifically the people listed here. Without their experience and advice, I wouldn't have gotten very far. So thank you. Next, please. So to start out, what is a debris flow? Why do we care about them? Water-saturated landslides that pick up things like gravel, silt, or large objects like boulders or trees that can be very destructive. Here's a picture of one in Switzerland, and they can travel long distances over tens of kilometers and at rapid velocities, so up to or over 56 kilometers per hour. We're not able to accurately predict when they will happen. We have ideas of triggers that could cause them, like rainfall or glacial melting or landslides, but we can't say exactly when these events will occur. So we need early warning systems in order to alert communities downstream that might be in the path of these destructive flows. Seismometers are often used for the early warning systems as they're able to detect the ground motion caused by the flows. And there's been a big push recently to try and link signals in the seismic waves to physical processes in the properties of the debris flows, like maybe volume or material composition. Next slide, please. Okay, so I'm focused on debris flows at Mount Rainier. And to clarify, so debris flows that start at a volcano can all be considered lahars, but for the purposes of this talk, I'm only going to talk about the largest events that are often caused by eruptions as lahars, where the small seasonal events are going to call them debris flows. And so we have here a picture of the lahar hazard map outside of Mount Rainier. And you can see in the brown is the lahar hazard zone, which extends all the way to Puget Sound in places. And this is because we have these deposits from previous lahars that have reached those locations. I'd specifically like to bring up the electron mud flow, which was the most recent lahar, happened about 500 years ago, and we don't have evidence that that was linked to any sort of eruption. So theoretically, this sort of thing could happen again, where we have this very big lahar that reaches very distant locations. And so in our early warning system, we want to be able to, again, link these physical properties of the debris flows to be able to provide warning if it is a small debris flow or a large lahar. And so we look at the small events to try and understand these links, if there are any. Okay, so next, please. And so I've outlined this area is Tahoma Creek that's in this box, and that's where our study area is. Next, please. Because this area has had 33 of these small debris flows since 1967. Here's a plot of when they happened between 1967 and 2020. And if you go to next, please. I've just circled this one to show that that's the debris flow that this picture was taken immediately after, and you can just see the pile of boulders and logs that have accumulated from the many years of debris flows in this drainage. Next, please. And so to collect the data, we've been putting out these temporary nodal seismometers, or nodes. They're able to record ground motion in 3 directions. They have the 35-day battery life, weigh about 6.2 pounds, and we can set them to record up to 2,000 ground motion samples per second. So they're really powerful little instruments, and here's one doing its job. Next slide, please. And so we deployed 52 of these nodes in Tahoma Creek, again, outlined in this white box. And if we zoom in on it, next, please. This is the installment that we did in 2023, where the red triangles are the node locations. The blue stars are clusters of nodes that we deployed that I've plotted to the right there. And then the yellow diamonds are permanent seismic stations that you will hear about later, I assume. And so of the 52 nodes that were installed, 36 were still active on August 15th to record this 2023 debris flow. Next slide, please. And so here's just some pictures of sort of the area of the debris flow. These are satellite images. The bottom of this sort of like fork in the stream is where the debris flow actually went through. So this is an image before the debris flow. And so if you go to the next slide, this is an image after the debris flow. You might have seen some differences, you might have not. I'll point out a few that I noticed looking at the image. If you go to next. So in this box, you can see that the channel texture kind of looks ropey from the material that was like moved in or out from the debris flow. And if we go back to the previous image, so next slide, please. You can see that that texture isn't there before the debris flow. And then I've sort of traced out the active stream channel at the yellow right above the Toma Creek suspension bridge there. And so if you go to next slide, you can see that it slightly changed. The purple line is now the active channel. So we can see some of these changes. We got a debris flow. It was non-damaging for any structures. So it was a win-win on all counts. Next slide, please. And so I'm going to show some of the data that we actually recorded from the debris flow. This is going to be data from a more distant station that I've circled here on the plot. Next, please. And so here on top, we have a plot of the ground velocity on the y-axis and time on the x-axis. And this bottom plot is frequency on the y-axis and time on the x-axis. This is the same data, but presented in different ways. And if you're not super comfortable with like frequency, you can think of a sound wave where high pitch would be high frequency, low pitch, low frequency. And then for power, a loud noise would be higher power. So in the brighter yellower colors, where a low sound or quiet sound would be in the purple or darker colors here. And so we can actually see the debris flow start in the frequencies here with this kind of like a smear of brighter colors down at the lower frequencies, which I pointed out here. And in the ground speed plot, you can see these the waves start to emerge slowly and gradually from this sort of background noise that's always happening, and then kind of roughly even out in amplitude and then die off as either the debris flow passed by the station or just lost energy. And so this creates like a typical sort of cigar or spindle shape that we see with debris flows in seismic recordings, which is cool. So we can, approximate the debris flow start time just from this distant station. Next slide, please. But with closer stations, you can get more detail about the flow itself. So if you look at this plot, which I have of a station that the debris flow passed directly by, it's circled here. And if you go to the next slide, this is what the debris flow signal looks like. We have a similar sort of starting time where you can see in the frequencies the debris flow start in these lower frequencies. But what's really cool with the closer stations is that you can see the ground speed start to ramp up as the debris flow passes right next to the station because seismic waves are going to be larger the closer you are to the source. And you can also see the same, this like smear of like higher power all throughout the frequencies that I have plotted here at the same time as this debris flow passes by. So if you have a bunch of stations that are deployed along a stream that the debris flow goes through, you can actually get, approximate locations based on these high amplitude peaks in the ground motion, and you can also get an approximate sort of velocity from that as well, because you know where they were approximately in time. And you can also, as I said, get some more details. So we have these like higher amplitude increases in the ground motion after this like initial debris flow front goes through, which is probably, you know, other pulses of this debris flow passing through. Next slide, please. And so what we'd like to do with this data, again, is to try and connect the seismic waves to these physical properties of the debris flow. And so some people have been working on that by using computational models, some of which include trying to replicate like impact forces from the particles colliding with the bed of the stream bed, and others have been trying to simulate like overall debris flow using like solid, liquid, or soil mechanics. So this schematic here is just an example of one of the models to replicate the impact forces. Either of these options would work for our data set to try and apply it to, and with the idea that we would be able to pull things like volume and be able to tell if if the debris flow signal that we see is going to be a large lahar that, you know, could potentially reach Puget Sound, or if its own damage is only going to be locally seen. Next slide, please. Yeah, so in summary, debris flows can be incredibly destructive. Mount Rainier has a long history of both local small events or large, widespread damaging events. We learn more about these debris flows by collecting more data, which is why we've been putting out these nodes to try and catch these debris flows in Tahoma Creek to hopefully be able to better provide information for debris flow warnings in the future. Thanks. Have any questions?
All right, excellent presentation, Avery. Are there no questions in the chat right now? Are there any questions that have come up? There we go. Taylor, did you adjust the alignments of your nodes to any point during the study, or at any point during the study?
We've been putting out nodes for 2023 was the only year that we got a debris flow, but we have been putting them out since 2020. So we've been slowly adjusting them. Most of what we've been doing has been concentrating more and more on Tahoma Creek because as the most likely source of debris flow at the moment.
Okay, any other questions? I'm going to ask one real quick. We did see a couple of odd little hydrologic anomalies, I would call them, not maybe debris flows, but July 20th, we had something that happened down that channel. Were you able to look, I'm sure if you had data from that point, but did you ever see anything else that, besides the August debris flow, that looked kind of unusual in that seismic record?
I haven't had a chance yet to dig into all of the data that we collected. So I've been mostly focused on looking at the August one, but I did see the July 20th thing at some of the stations. Yeah.
Yeah. I was trying to figure out what that was when we noticed it. So
yeah.
Another user asks, how will your lahar results inform public safety plans?
Yeah. So again, we're hoping that so the idea is that hopefully with combining the debris flow properties with like the seismic data, if we are able to provide quicker warning for areas downstream, because right now it's just kind of a trigger that, oh, there is a debris flow happening, and we have to sort of manually go in and try and figure out what we think it's going to do. So hopefully by combining some of combining the seismic waves with the properties of the debris flow, we could hopefully give more warning time, which is the strongest thing I can say about how that would inform public safety plans, is just hopefully provide more warning time.
All right. If there's any other questions, you can leave them in the chat, and maybe Avery, you could answer them directly from there.